All right, let's continue on with vectors. This is part 2. Remember, we left off with the decomposition of vectors. We're using right triangle trigonometry. Let's continue on with this. Here is a vector, vector A. We want it, it's in a coordinate system, an xy coordinate system. We could label this as the origin, and the tip of here would have an x coordinate and a y coordinate. The x-coordinate would represent the x component, and the y-coordinate would represent the y component in terms of its magnitude. We'd want to decompose this, though, into its x and y components. So let me go back to doing that. Here's a vector. It has a magnitude of 1.50 meters. Its direction is 25 degrees. And if we made this north and this east, this would be 25 degrees north of east. But how do you get the components? Well, to get the x component, you would take the magnitude of this vector and multiply by, remember, the cosine of 25 degrees. Make sure you're in degree mode. And to get the y component, you'd take the magnitude and multiply by the sine of 25 degrees. If you do this on your calculator, you'll get these answers here. You'll get the length of the sides of a right triangle. Now this would be 1.36 meters x hat, and this would be 0.634 meters y hat. Notice I could go back and get the magnitude of the original vector by using the Pythagorean theorem. 1.36 squared plus 0.634 squared, and then take the square root. And I could get the angle here by using the inverse tangent, or the arctangent, of 0.634 meters divided by 1.36 meters. I get the angle, which was, 25 degrees? Excuse me. So, when you're doing this sort of thing, when you're breaking up a vector into its components, you have to be conscious of what quadrant your vector's in, because remember, in different quadrants, x can be either positive, negative, and y can be either positive and negative. And those represent the components. When you're in, say, if you look at part A here, the vector's in this fourth quadrant, 1, 2, 3, 4. This is where x is positive, but y is negative. You have to know y is negative, so when you're adding the components, when we add, you do vector addition, you have to know that that's negative, because it'll be subtraction. So whatever quadrant you're in, it'll determine if x is positive and y is positive, the components. We talked about this in class. So let's look at this vector A. Notice I could think of it in terms of this acute angle. Its x component is a cosine theta, and its y component is a sine theta. But if I reverse the angle, if I use the angle up here, theta prime, which would be equivalent to this side, which they're showing here, notice that the y component becomes cosine and the x component becomes sine. You have to be careful what angle you're using. There's two acute angles in a right triangle, and I'm trying to use the one with respect to the x-axis. If I use the one up here, which would also be the angle with respect to the y-axis, if you remember your geometry, you'd have two parallel lines right here and right here, cut by a transversal, and these would be alternate interior angles, and they are congruent. Anyway, be careful what angle you're using when you use sine and cosine. It could be reversed, like in this case. But they're equivalent. You get the same thing. So when you add two vectors, A and B, you want to find the components of each one. Find the x component of A and the x component of B, and you would add them together. And its direction would be x hat. Now, if this comes out positive, it's in the positive x direction. If it comes out negative, it's in the negative x direction. And the same thing for the y's. You find the y component of A and B, and you add them together. If it comes out positive, it's positive y hat. If it's negative y hat. And then to find the resultant vector, you take the net x component, call it r sub x, and the net y component, when you add these up, r sub y, and you could write it this way. You could also use these values to figure out the magnitude by applying the Pythagorean theorem. And you could find the direction of the resultant vector r by using the inverse tangent. And you could add any number of vectors this way. If you had a c vector, you do ax plus bx plus cx, x hat, plus ay plus by plus cy, y hat, and so on. And this always works. It's not necessarily the best method depending on the situation, but this component method always works. It gets tedious after 3 vectors, though. Typically, we use this for 2 or 3 vectors. All right, here is a vector right here, not labeled, but it has a component here, an x component of 3x hat and a y component of 4x hat. And I want to find the original vector. Well, you should recognize that as your 3, 4, 5 right triangle. And if you don't, you could write the vector, call this vector A, as 3x hat plus 4y hat. And how do you find the magnitude? Well, you apply the Pythagorean theorem. You can write it out in vector. This is vector notation. But you could also write it, and you probably did this in your geometry class. You use these chevrons. And another way to write vectors in geometry notation from the old days is to use these chevrons and put 3, 4, which is the coordinate at the tip of the resultant vector. And it's understood that this always starts at the origin, and you draw a line to this point, and you put an arrowhead on the end here, and you have your vector. So I could use this notation. This isn't used in our textbook. What's used in our textbook is the standard vector notation up here. But I like this simple way of writing it from geometry. So what we did, it was we can take this vector. I put a little s on it to mean I'm decomposing it, replacing it with vector b and vector c, which is the x and y component. That's typically what we do. And vector a is actually the sum of vector b plus c, if you use the tail to head method. So vector addition, we add the corresponding components. Here's that formula again. Oops, let me backtrack. Vector a plus vector b. This would be Rx, Ax plus Bx. This is Ry, Ay plus By. Let's look at some more of this math here. If we want to do subtraction, we just subtract the components as such. If it's A minus B, it's Ax minus Bx, x hat, Ay minus By, y hat. Scalar multiplication, same thing. We could represent the scalar as k, and k times the vector is equivalent to k times each component. So k times the x component and k times the y component. For example, if we had vector A represented in this vector notation as 2x hat minus 3y hat, and vector B as minus 4x hat plus 2y hat, we could do the vector addition in this way. We take the x components and we would add them, 2 plus a minus 4, x hat. Take the y components and add them, or you could think of it as subtraction. Remember, subtraction means add the opposite. You get minus 3 plus 2. And what's left over? Well, here we get minus 2x hat. Here we get minus 1 y hat. There's your answer for the sum. For the difference, it's subtract. Remember, it means add the opposite. But 2 minus, well, what's b here? It's minus 4. You put it in there. But what will happen here? Be add the opposite. So this will be 2 plus 4. You get 6. And over here, same thing with 3 minus, well, what is the y? It's a plus 2, so it's still going to stay, it'll be minus 2 still, so you get minus 5. Let's take a look at that. And then scalar multiplications is pretty straightforward. 2 times the x component, 2 times the y component, you get 4x hat minus 6y hat. There you go. All right. Here's a little bit more complicated formula here. We got vector A plus 3 times vector B. Well, you do the scalar multiplication of 3 times the components of vector B. And you add A to it. So if you look at vector A, 2x hat minus 3y hat. And B is negative 4x hat plus 2y hat. Well, let's see what we got here. Is this correct? Well, you got the components. You got 2 from the x hat, and then 3 times negative 4. That's the first part, x hat. And then we do it again. We have the y part, negative 3y, and then 3 times the 2 here. So for the x part, we get negative 10, and for the y part, we get 3. Yep, that looks good. All right, let's do another one. Oh, the other one's got disappeared on me. Well, let me just sum this up. Magnitude of vector, here's the vector notation. That would represent vector A. This is the x component. This is the y component. Notice magnitude and direction, magnitude and direction. For example, this could be 3x hat plus 4y hat. And then there's the direction of that vector. You could write this in vector notation, right? Ax with the arrow over it, and it equals its magnitude and direction. Ax, x hat. This could be, as I said, 3x hat, and this could be 3y hat. It's the coordinate at the tip of the vector. So that's component notation or vector notation. And remember, you can get the x component and the y component when it's set up like this using the sine and cosine. It's the magnitude. When we drop the vector symbol, just write a instead of a with the arrow over it. We're talking about the magnitude of the vector. Well, I could put absolute values around here if I left the arrow in like we did before, but it's not necessary. And then to get the magnitude of the vector itself, we use the Pythagorean theorem. But here's the notation for the magnitude, just the vector A with no arrow, or with the absolute values around it if it has the arrow, or you could use a double absolute value. You do this in pre-calculus. And then the angle, the inverse tangent. All right, I think this is a good place to stop, and we'll talk more about this later.